example, we're going to be working with a different substance, polonium-210. The half-life of polonium-210 is 140 days. How long will it take for a sample of this substance to decay to 20% of its original amount? Understanding that it's going to follow exponential decay, we can begin our work with the formula for exponential decay, A equals A sub 0 e to the kt. We first need to figure out the rate of exponential decay for polonium-210, knowing that its half-life is 140 days. Filling in the formula with the pieces that we know, we don't really necessarily care what the starting amount of polonium-210 is. We're trying to figure out the rate of decay, so we're going to leave K as a variable. And we know that the half-life is 140 days. Half-life means that in that time period, in the 140-day time period, half of the original amount, which is the A sub 0, will have gone away. So we know that our end amount that we're going to put on the other side of the equal sign needs to be half of the original amount. Basic algebra tells us that we can divide both sides of the formula by A sub 0, which is the reason why I said at the beginning that we didn't really need to know what that initial amount was. We rearrange the we rearrange the power so that the 140 is first, and then the K is second. Not that it necessarily matters, but that is the convention. We are trying to solve for a variable that is locked into the power of an exponential. Feels like a situation where the natural log might help. So we're going to take the natural log of the left side, and we're going to take the natural log of the right side. Now, using whatever algebra mental gymnastics you want to use, this right-hand side, because you're taking the natural log of something that already is to base e, is just going to be left with 140k. That's our trick for getting variables out of the power into something that we can solve through more conventional means. We finish by dividing both sides by 140, and we get that k is equal to the natural log of 1/2 over 140. Now, depending upon the calculator that you use or computer that you use and the specificity with which it can show a decimal, if you typed this, you might get an answer that looks like this, written in scientific notation. Now, we definitely need it to be negative because we need to show that the rate is a rate of decay, not a rate of increase. But we're also going to need to type this number, and it's a little tricky to type something that's in scientific notation into the broader formula that we're going to use. So it might benefit us just to have a representation of this number, despite the fact that it has some zeros in it, that is the decimal representation and not the scientific notation. This is going to be our rate of decay when we go back to that original formula and work with the amount of polonium-210 that we're trying to find. So now that we have our K for polonium-210, we can transition over to finding how long it will take to get to 20%. So similar setup as before. Again, not super interested in the starting amount. We're going to see why in a second. We now have the rate of decay, which is negative 0.00495. And we're going to be interested in determining that length of time it takes to decay to 20%. That variable in this example is a representation of days. We're working with all of this in days. You might see examples that are instead where t represents a number of years. That's okay. Process is still the same. Now again, we're not super concerned what this actual number is because on this left-hand side, we want to get to 20% of that original amount. So we're just going to say 0.2 times a sub 0. That's going to be our representation of the 20% of the original amount. Again, basic algebra, we're going to divide both sides by a sub 0, and we're left with 0.2 is equal to e to the negative our rate of decay and our amount of time. You can see the similarities between this line and that line of figuring out what k is. We couldn't go into this question with two variables. We couldn't go into the question not knowing the rate of decay and not knowing the amount of time. The whole point of the question was to figure out the amount of time. So we first needed to figure out k, but that doesn't mean that the steps aren't going to be very similar to the steps that we had before. Again, let's take the natural log of both sides. And again, because you are taking the natural log of a term that has base e, that's going to leave us with just that power. We're figuring out the number of years. We divide by both sides by that rate of decay. And you might be concerned that we're going to end this with a negative number. You might be thinking, oh, the natural log and then divided by a negative, our answer is going to be negative. Well, the fact that the natural log is going to produce a negative on its own is a good sign for us, because that negative will interact with the negative from the denominator and leave us with an answer of approximately 325.14 days. Now, a couple things to keep in mind. First, this is an approximation on all accounts. This is an approximation because it's a non-terminating decimal that we made a decision to round. This is an approximation because that number was a non-terminating decimal that we decided to round, and that number was a non-terminating decimal that we decided to round. So this is not going to be a perfect representation of the amount of time to get to 20%. If you have the ability to maintain more decimal places, you could probably get a more exact answer, or you might even get a slightly different answer. If you carry along more signs, you might get a slightly different answer. If you take the, oh no, I'm sorry, not signs, decimal places. If you take that and make that the denominator, you might get a more precise answer. So don't panic if you're using a slightly different technology that's giving slightly different numbers. This process of finding approximations based on exponential functions only works if we all sort of understand that it's not going to be perfect. It is just an approximation for how long it would take. And even this 20% could be considered an approximation as well. So following the format, we figure out what that rate of change is, the rate of decay for the variable, or for the amount of the substance, figuring out that variable first, then using that value to determine our amount of time it would take to reach some other specified amount.